Please welcome Jeff to the stage, who's here to help us solve the mystery of index use. And later in this presentation, we'll have Jeff feature a customer spotlight where we'll have Chris Chen and Tina Varghese from Condé Nast. Thank you. Welcome, Jeff.
Awesome. Thank you, Gianna. I got that. Yep. Thanks so much, Gianna. Hey, everybody. Thank you so much for being here. Thank you so much for coming. So today, I get the pleasure to present the Demystifying Indexes presentation. This is a presentation from Asya Kamsky. She couldn't be here today, so you were lucky enough to have me present this. We are going to demystify MongoDB indexes. Once this clicker starts working, though. Okay. So I think there's a slight lag. Hold on for technical issues. In just one moment, we'll get started. Okay. All right, so we're going to demythify, as Asya says. We're really here to demythify the myths that surround indexes. There's a lot of them. We're going to get into some really interesting detail about indexes in MongoDB. But we're going to bust some myths today, as Asya says. So what is this talk about? Probably the best way to talk about what this talk is about is to talk about what it's not about. And so this talk is not about tips and tricks in MongoDB querying, tips and tricks for querying MongoDB with high performance, explain plans, the sights and smells of a bad query. We've got lots of great presentations on how to write good queries in MongoDB, but we're going to really focus in on the indexes that are required to support those queries, but not how to write those queries. And hopefully by the end of this presentation, we're going to have a good understanding a better understanding on how indexes work in MongoDB and a little bit of details and nuances around them. As Asya likes to start her presentation, she uses analogies. And as she says, it's a really great way to kind of explain concepts in a more visceral, tangible manner. I picked this. Does anybody know what this thing on the left is? Right? Yes. It's a library card catalog, right? Some last century technology for sure. They started to get phased out in the late 1980s, early 1990s, and be replaced by computer systems. But I want you to envision a card catalog and the value that the card catalog provides. So imagine we walk into a library and we're trying to find a book. Maybe it's The Fine Art of Literary Mayhem by Merrick Land. And we walk into the library and there are 1,000 stacks of books. And imagine trying to find that one book without the card catalog that tells you the section of the library, the stack, and the Dewey Decimal number on the shelf to be able to find that book. I put under here just kind of for ha-has. And if you folks ever remember, we had book cards, but we also had author cards. And there's an example of an author card from J.D. Salinger. And this is really kind of an interesting analogy because it really is sort of like what an index in MongoDB is. You know, imagine without an index, you've got to scan through those 1,000 stacks of books to try to find what you're looking for. And this is what the index really does. It gives us a shortcut to find what we're looking for and find what we're looking for relatively quickly. So what we do the work beforehand. We organize and carefully label things. And we do that so we don't have to do the work afterwards. Look through everything to find things. And this is a trade-off, and we're going to get into some of those trade-offs of what we do in terms of the work that we do beforehand and being able to not have to do that work afterwards. So we're going to get into MongoDB performance, obviously. We're not here to talk about libraries and library shelves and books or the fine art of literary mayhem, but we are here to talk about achieving better MongoDB performance with indexes. So let's say we have an orders collection, and we're going to execute our query. Again, we're not here to write the query, but let's say you've got a development team, and they've got this big orders collection, and some developer has written a query, db.orders.find, and they're looking for the order ID that matches the order ID of 295. Without an index, in MongoDB, we have to scan through every document to find that order ID. We would have to look through every single document in the orders collection. In addition to looking through every single document in the MongoDB orders collection, we'd actually have to read through every single field in every single document to be able to find what we're looking for. Because without an index, we can't even tell exactly where in the document that field is. So the time that takes, obviously we call that a collection scan. And for this presentation, we're going to consider the time that it takes to query the database without an index, order n. Okay, that's our time, order n. So how can an index help? Well, let's talk about what an index is and how can it help. Well, an index is a data structure that's in the database. The index itself is actually stored in the file system along with your collections. And that index is probably, if you're using MongoDB, it's most definitely a B-tree index. In most relational databases, this is the most popular type of index, is a B-tree. A B-tree is a self-balancing data structure. It maintains sorted order of data and allows for various operations to be executed in what we call logarithmic time, so log time. And so here comes the first myth. Does anybody know what the B in B-tree stands for? Does anybody think they know? Shout it out. Balanced. That's the most popular opinion, balanced. Well, it actually turns out we don't really know what the B in B-tree stands for. Balanced is the most popular opinion, but the creators of the B-tree index never told anybody what B stood for. Some people think it's balanced. Some people think it's binary. We're going to kind of disprove why it's not binary. Some people also think it's Boeing because the creators of the B-tree index were working at Boeing at the time when they developed this. Turns out we don't know. Balance is probably the best answer that we have. Turns out we don't know, though. Okay, so order ID 1, if we have a query that says, give me order ID 1, this is actually what the B-tree will look like. We have a root node, and then we have leaf nodes down at the bottom, and the leaf nodes contain the values that we want to traverse through to find the order ID that we're looking for. And as you can see, it definitely doesn't stand for binary because those are not binary values. Those are human-readable numeric values. So if we traverse through this index and we get to the index entry that we want, that index entry also has a record ID. And the record ID is actually going to be an ID that gives us a pointer to where on the file system disk that record exists. Where does that actual document in that collection exist? Once we find the index lookup, we get the record ID, we can now go down to disk, retrieve the document, render it to the query. If there's multiple orders that match order ID 100, we might actually have multiple record IDs in that single index entry. And those record IDs point us to the file system, point us to where we can go and grab those documents. If we have a range query, let's say we had order ID 150 through 250, what we would do in the B-tree is we would read through the B-tree index starting at 150, and we would read any entries that we find. And when we get to the end and we hit 250, we're going to stop. We're going to stop reading the index. We're going to go from 150 to 250, and along the way we're going to pick up those record IDs, and that's going to give the storage engine the ability to now go down to the file system and potentially retrieve those documents. So that gives us an order of magnitude speed difference between a collection scan. And let's call this order log n. So in logarithmic time, this is a huge advantage. We can go from 20 seconds, 30 seconds, multiple minutes scanning through a collection to doing that in sub-second response time. So this is not the only advantage, actually, in MongoDB of the index. Not just the advantage is not just speed of your query, but if we read the entire collection, we've got a couple problems. And those problems really kind of relate back to the WiredTiger cache. So the MongoDB storage engine is called WiredTiger. It uses database RAM, server RAM, And it reserves usually typically about half of the server RAM for its own cache. So if you have a 32 gig RAM server and you deploy MongoDB on it, you get 16 gigs of cache available. And in that wired tiger cache, if we do a collection scan, we got a little bit of a problem. So if our collection has to be scanned through, MongoDB actually, just like any database, any typical database, has to read the entire collection into that cache. And it's possible that you could have more, your collection size actually might be larger than the available RAM to cache. And so the problem here that we have is not only are you going to get a collection scan, but as Asya says, you're going to thrash your wired tiger cache. So if you have other operations, other people, other developers, other applications are querying the database at the same time, well, as soon as I hydrate that collection into cache, I'm bumping everybody else out. And it's also possible that the collection is larger than the available cache, and so what I end up having to do is page through it and do a lot of disk to RAM swap. And so my query is going to be slow, but I'm actually going to slow down operations for everybody else that is executing threads inside the cache at this one point in time. So here's a question, and here comes our first myth, and this is related to performance. So, okay, so is it a myth or is it truth that your entire indexes have to fit into wired tiger cache? Who thinks that it is myth that your entire indexes have to fit into cache? Okay, it's pretty good. Who thinks it's truth that your indexes have to fit into cache? Okay, well, sorry, it's a myth. So only the index pages that are being accessed at any given point in time have to be read into wired tiger cache. So if you have a really large index, if you've got 1 million records in your collection and you have a really large index, and I'm only looking for a small range, order 150 to 250, only the leaf nodes, those pages in the cache, the pages in the index, only those leaf nodes have to be read into wired tiger cache. I don't have to hydrate the entire index definition, the entire index into the cache. Okay, so let's talk about a right-balanced index. This is a super important concept here in the B-tree index called the right-balanced index. Good way to describe it, probably visually here, is let's say you have an orders collection, again, and you're processing retail purchases, and you have active orders, and you have orders that are in process. Go back one. So if I have active orders, I'm probably creating order IDs. I'm probably creating those IDs that are monotonically getting larger, kind of increasing monotonically. I probably can do that on order ID. I can do that on customer ID. Like if I create a new account, I'm a retail application, and if I create a new account and I assign a new customer ID, I'm probably assigning a sequentially higher ID. Or if I'm processing orders by order ID, each new order gets a higher ID. What that means is my older customer IDs or my older order IDs are going to be on the left side of the index and not really accessed very often. So it's very likely, like in a retail scenario, that my most recent orders are going to be the ones that are most active. I could have 1 million orders in my collection, but only like 5% of them are being accessed at any one given point in time. So then the active orders, the higher order IDs, are going to be on the right side of the index, and this is known as a right-balanced index. We get a right-balanced index when we use monotonically increasing values like order ID, object ID. The opposite of this kind of right-balanced index is if you're using random values, like some random UID, things like a UUID, some random ID, or a hash of an ID. And what happens in that scenario is that the database, when it reads the index, it's not going to only read just the leaf nodes, the pages on the right side of the index. It might actually start to access and traverse through random points in the index. And you get a lot of random reads. And what happens in that scenario is we probably have to hydrate the entire index into wired tiger cache. We can't just pull the pages that are most active and most called for and put those in the index, we probably have to put the whole index definition in. And again, you've got other operations in the database, things like queries, other indexes, other threads occurring. So a right-balanced index is actually going to give you much overall better performance in the database, in addition to that query being faster and not doing a collection scan. But this is a good time to remind us all that there is a trade-off. These indexes are definitely not free. So this is a great thing. I'm not going to thrash my wired Tiger cache. I'm going to get better query performance, but the indexes are not free. And so when we do the work before and we create an index, documents are indexed at write time. So let's say I have a customer collection and I've got 3 indexes on that customer collection. Well, what we actually have to do in the storage engine when we insert or update a customer record, we insert and update, we write the collection, the document to disk. That's one IOP, but then we actually have to write entries into the 3 indexes that exist for that collection, and that's 3 more IOPs. So the more indexes that we have, the more IOPs that we incur, because the database, the storage engine has to do more operations. It's got to insert the record, the collection, the document in the collection itself, but then hit every index that's appropriate for that collection. And if we don't do the work ahead of time, we do the work after, obviously we're doing full collection scans. We definitely don't want to do that, but it's a trade-off. So you don't want to have an exorbitant amount of indexes on your collection. We're going to get to some of the tips and tricks around that. So your writes will be slower. Again, that order log n is better, but your writes will obviously be faster. If you have no indexes on your collection, it's just one IOP. I don't have to write to an index. I just write the document to disk and I'm done. Your writes will be super fast, but your reads will probably be pretty poor. All right, so let's talk about types of indexes. We're going to talk about really just the B tree today. It's impossible to not hear about vector search indexes and text search indexes these days. We're not going to talk about those today. We do have those obviously in MongoDB. Those are not B tree indexes. Those are actually Lucene indexes. The B tree indexes have different types. You can have a simple index, which is just the one ID that we index. You can have a compound index where it's order ID, last name, city, state. You can have a wildcard index, sparse index, a partial index. I'm going to talk a little bit about parse indexes today. But I want to talk about a concept that applies to all of them, and that's cardinality. The term cardinality in the database world simply means how many unique or distinct values do you have on a particular field. You know, is it someone's last name? We all have very different last names, so the cardinality is high. But you know, maybe we are all either, I don't know, let's say we are all either above or below a certain age. That would be 2 values, one, you know, yes or no. A binary value like that could be incredibly low cardinality. The number of US states is 50, so that's fairly low cardinality. So let's say in our order collection we have status, processing, or done. We have 2 values, only 2 values, so cardinality is very low. So this gets us to the next myth. It's a bad idea to index a low cardinality field. Who thinks that's true, that it's a bad idea to index a low cardinality field? Any takers? Okay. Who thinks it's a good idea to index a low cardinality field? Okay, pretty good. Well, it's actually a myth that it's a bad idea, and we're going to get into a little bit of the reasons why. So whether you're querying, it's actually not the cardinality that matters, it's the selectivity of your query. And so we're going to get into that, but let's say you have an orders collection, and I have 1 million orders again in that collection. Only 5% of them are in that status of processing, and the other 95% of those 1 million records are in done. If I don't have an index on that field, I've got to do a collection scan, but I've got to read through all 1 million records in addition to the 5% that I really care about. I've got to read through just so many more records than I have to. So it's definitely a good idea to have an index on low cardinality fields. And again, as I said, it turns out it's not the cardinality, it's the selectivity of your query. If you're selecting on very low cardinality fields, you still want an index. And so this brings us to another myth related to selectivity. Is it a myth or is it truth that a $any or a $not equals, an inequality condition, cannot make effective use of indexes. Turns out this is actually a fairly common opinion. Who thinks it's a myth that not equal cannot make effective use of indexes? Anybody? Who has the eye? Who thinks it's a truth? Okay. It's a myth. Another myth has been busted here today, here in New York at MongoDB, MongoDB.local 2025. It's a myth. And the reason why, it's about selectivity, but it turns out that when I query the database with not equals, I'm still using a selectivity, it's still selective, and I'm still using an index, but we're gonna process this a little bit differently than if you say, give me all orders where processing is, all orders that have the status code of processing. That's a very explicit query. I can go right to the index entries that I care about. If it's not equal, we're actually gonna process that as a range query with WiredTiger. We're gonna step through all of the index entries, and we're gonna find everything that does not equal done. Any other status codes that might not equal done. And so we have a slightly broader range of things that we're gonna look for. It's not quite as selective, but it turns out it's gonna be actually almost as fast as a query on status equals processing. So here's our min key done, and our max key is done. We have to query that as a range in the WiredTiger storage engine, but it's actually almost as fast. So not equal $any, can use an index. You should have an index on those fields. And so let's talk a little bit more about these compound indexes now. So let's say I have a country, a state, and a zip, and I'm executing this following query, db.collection.find, where country is US, state is New York, zip is 10001. So we're always going to query on these three things. And the country is mostly going to be US. We're mostly going to be looking up US orders. And the states can include all 50 US states. And there's about 42,741 US zip codes. So our cardinality on country is probably the lowest, state next, and the highest cardinality is zip. So what fields and in what order of these fields should we put the index in? All right, so option one, again, our query is db.collection.find, country, state, zip. Option one, should we put an index on country, state, zip? Or should we put an index on zip, state, country? Who thinks option one? Okay. Who thinks option two? Okay, well, actually, turns out these guys are going to be equally as fast. So not only can MongoDB read an index forward or backwards, as long as you come in with what we call the top level field, either the prefix or the suffix of the index, if you come in with one of those fields, MongoDB can read an index forward or backwards. But they're equally as fast. And the reason why they're kind of equally as fast is how we store the data in the B-tree index itself. So if we had state and zip on our index versus zip and state versus country zip, this is what these index entries look like. By the way, we don't store the fields in the MongoDB indexes. The indexes themselves only have the field values because we can get the field values from the index definitions themselves. Another interesting thing to note is that we can actually serve up the data just from the index and not go to the file system and retrieve the MongoDB document itself. We can synthesize the query and the data from the index entries alone. If you come in and you're only querying on fields that exist on the index, we don't actually even have to go to the file system. We can serve up the documents right from the index themselves. But this is not the reason why these two queries are equally as fast. So, two options, country, state, zip, zip, state, country. If we look at the B-tree indexes, the B-tree entries, the speed of the query, the speed of the retrieval of the entries from the indexes depends upon the depth of the B tree themselves. And then in either example, these guys have the same depth, right? So whether I go country state zip or zip state country, I have the same depth in the B tree, so it's equally as fast querying the boat. But I'm going to tell you something. We actually prefer option 1, country state zip. And it's not because the query comes in the order of country state zip. The reason why we do that is the cardinality. This is something actually pretty neat. So prefix compression. In MongoDB, the first field, which is known as the index prefix, gets compressed. And so the index size itself becomes smaller when we can execute compression on it. And as we know, like low cardinality fields compress much better. If every value is yes or no, or male or female, or if I've only got one country code, a low cardinality field, I'm going to be able to compress that much, much better than a high cardinality field, like something like last name or a zip code. And so the index entries actually get much smaller. We think that's about a 30% size reduction in the size of each index. So again, going back to that wired tiger cache, if you've got a lot of indexes, it's in your best interest to put your low cardinality fields at the beginning of the indexes. But all things are seldom equal. So here's a myth or a truth. All equality must put high cardinality fields first. Anything that's an equality condition must put the high cardinality field first. We've actually kind of busted that one already, right? So that's a myth. So what's interesting here, again, if you come in with a top level field, MongoDB can read the index forward or backwards. But for your developers who are out there building indexes, things that I've seen a lot are developers will build an index on country and state and not realize that I can have one index that serves all of these needs. If I build an index on country state zip, I can query on country alone, I can query on country and state, I can query on country and state and zip. I can actually query on country, skip over state, and then read zip if that's my query. So I can skip over fields in the index so long as I come in with the prefix or the suffix. I can read it forward or backward, and I can skip over fields. All right, next one, myth or truth. ESR is a rule. If you folks have read our docs, you know that ESR is equality, sort, range. So we want to put our equality conditions first, our select conditions next, and our range conditions at the end. There's actually a talk that we gave a number of years ago where people said this was a rule, but it was done in air quotes, as Asya says. So it's actually a myth, it's a guideline. I'm not gonna ask everybody. This is actually a guideline. And the reason why it's a guideline is that ESR is really not necessarily, we'll get into this. Bless you, as long as I put the E first, I can have S or R and then S, as long as I put the equality condition first. And the reason why I want to put that equality condition first and not the R or the S, I don't want to put a range field first or a sort field next, or sort field first rather, sorry, is the equality conditions are going to allow us to retrieve the documents, the index entries from disk, and those index entries are going to be in sorted order. And this is how the database engine stores the B-tree indexes. If we have an equality condition, all of the rest of the fields are going to be in what we call as sorted order afterwards. So is your query range selective? Then you probably, if your query range selective, then you probably want to put equality first, range next, sort next. If your query is not selective, you probably want to follow the ESR rule, where it's equality, sort fields, and then range fields. So let's get back to this low cardinality situation just for one moment. So if I'm status code processing country, France, order date greater than ISO date 2024, April 30th, I want to make this a compound field. The first two fields are not equality, so order's not going to matter here. But if I have status, country, and order date, this is really what I probably want in my index entry, status, country, order date. I'm going to get the same benefit of a right balanced index. But here's something really interesting. I know I said that you're coming in and you're building a right balanced index if you just use these monotomically increasing values like order ID. But it turns out if you've got an order collection, you're coming in and you're creating orders, those orders get fulfilled, and the status goes from processing to done. And the problem with that is that you're going to probably end up moving all of that data to random places in the index. And so we want to use a partial index. And this is the last index entry I'm going to talk about, is partial indexes. If you use a partial index, you can actually specify in your index definition, which we see at the bottom, an expression that says only index where status is processing. So I don't have to fill the index entry up and go back to the index and constantly update it and have that index have 1 million orders in it, where the only thing I really want to query and care about is where status is processing, and I don't care about status done. Just don't put that status in the index entry. Do a partial index entry, and that's going to give you kind of that right balanced index that we're looking for, and you're not going to have to go back and update the index to done and then have it kind of hit some random part of the index. Okay, so this is the point I'm going to stop. I've got two really great people coming up on stage with me, Chris Chen and Tina Varghese. Chris and Chen, if you can join us on stage, and I will grab you your chairs. You got them? Excellent. Chris, Tina, thank you so much. Chris and Tina join us from Condé Nast. Obviously, we know each other. The folks in our audience don't know you, so Chris and Tina, if you don't mind, could you introduce yourselves and tell us a little bit about your roles in Condé Nast?
Sure. Thanks, Jeff. Thank you so much for having us. Thank you to MongoDB for inviting us here. It's a really wonderful opportunity. We're excited to be here and tell a little bit about our story. My name is Chris Chen. I'm the VP of Architecture and Governance at Condé Nast, so I'm responsible for all of the technology systems at Condé Nast, both internal and external. I'm also responsible for all of the data governance. And I got started in my career working as a consultant in the Bay Area, helping companies build out their own solutions, custom solutions for them. And it really taught me the value of workflows and how critical it is to make sure that the end-to-end of the entire workflow is covered by any solution that I architect. So about a third of my career was spent doing that, and then the other 2/3 have been spent applying that mostly to companies in the content space, helping media companies build better content and distribute it more widely. So that's a little bit about me. Tina?
Hi everyone, I'm Tina. I'm the Director of Engineering at Condé Nast. I lead both strategic and engineering initiatives across customer data platforms as well as MarTech teams. Over the course of my career, I've spent a lot of time building scalable microservices, but at the core of it all, it's always been about content and how people experience culture through content. Thank you for having me, and I'm excited to be here.
Yeah, thanks, Tina. Thanks, Chris. So I know that you both have been working on some really exciting things inside Condé. Can you give us some insight, I guess, on what you've been up to over the last year or so with the team?
Sure, yeah. I think it's a very exciting time for all companies, regardless of which industry you're in. One of the most exciting things I've been part of for the past couple of years is I've been working on an AI task force that has really been trying to figure out what the AI strategy for Condé Nast should be. You know, what types of AI projects should we invest in? How should we deploy them out? What's going to bring the most value to the company? And we've put together an AI governance framework that categorizes projects into 3 different buckets. The first is around bringing productivity and efficiency improvements to the organization, making our workers more productive, helping them get more things done more quickly. The second bucket is around using AI to enhance an existing business advantage. So we may feel like we have a competitive advantage in a certain area. How can we use AI to extend that advantage? And then the third bucket is really around what I like to call innovative things, things that people haven't seen before, new revenue streams, new experiences, new areas that are a little bit more speculative, but I think very interesting. And part of the reason we created this AI framework is to ensure that we were able to spend time across all three of those categories. We didn't want to say, oh, we're going to spend all of our time only on employee productivity and efficiency. We feel like a good strategy encompasses room for all three of those, including things like innovation, which might be a little bit more speculative and a little bit more risky.
Yeah, and Tina, you've been, some of those innovations in that AI framework, you've been on the front line for, right? Can you tell?
Yeah, absolutely.
Can you tell us a little bit about them?
Yeah. So I'll go into the entire detail. So when I first took over recommendations, the primary initiative at the time was to move to Roberta embeddings. The idea was that Roberta understood context a lot better, so our content recommendation should in turn be better. So we put Roberta embeddings onto our existing tech stack, which was Elasticsearch at the time. We created a new strategy, put it behind a multi-arm bandit, and let it run in production. And really nothing happened. So with all our AI initiatives in the pipeline, we knew that it was time to look at alternative solution. And with our existing limitation, we had to. Yeah.
So you had some challenges.
I definitely had a lot of...
So it wasn't an easy path, correct?
It definitely wasn't an easy path. So going back, once we put things onto Elasticsearch, our P95 latency for our API response time shot up to 800 milliseconds. Our embedding relevance itself was weak. And really the constant re-ingestion and bulk processing led to a lot of operational complexity and cost. And really just to stay afloat, we kept on adding more and more data nodes. And inevitably we had a couple of outages. And that's when we really started looking into MongoDB as our vector search. The documentation was pretty good. The developers were already familiar with Mongo, so I was comfortable with it. And the Mongo experts were always there to help us. Shout out to Mitch. He helped us through the entire journey. And really the turnaround time was 48 hours for the MongoDB experts. Long story short, so we had the metrics were pretty impressive. Our P95 latency went from 800 milliseconds to 80 milliseconds. Our CTR shot up dramatically by 35%. And really the part that my VP was most happy about was that we brought down the cost by 65%. And this project has really been one of the most impactful projects that I've done at Conde. It really brought the team morale up a lot. The lead engineers were really firefighting at the time, just keeping the Elasticsearch, keeping the recommendation services up. So we freed up their time, and they are able to build a lot of the new AI initiatives that we have on a stable platform. It's been a great journey so far.
Yeah, that's great. So software execution velocity, pretty important, right? The ability for your teams to move quickly instead of firefighting.
Exactly.
Yeah, I think until you live that, it sounds like words, but once you live it, it becomes pretty real, right? Chris, what's next? Given that, your business folks must be thrilled, by the way.
Yeah, for sure. But as with everything, once they see something good, they want more of it, right? A big part of the challenge we found with all of our AI-related initiatives and recommendations in particular, and vector search, is that we've built 3 of these pipelines now, and what we found is that each of our brands at Condé Nast all want different strategies and different flavors for their vector search. So some want a specific type of embedding model because their content is a certain type and we have to cater to it in a different way. Some of them want to augment it with additional metadata. Maybe we have to run it through a classifier. And sometimes they want to augment it with completely unrelated information like customer data or product catalog information that they want merged into those results. So what we found is that the complexity of the actual vector search solution is complicated because of these different strategies and different approaches that each of our brands have. And at Condé Nast, we have over 70 websites. So you can imagine that if we have 70 websites, all with their own content, that all want a different strategy for rolling out vector search and AI capabilities, it's going to get very complicated for us to manage all of that. So the next step for us is to build out a platform that really enables us to do this at scale. It really enables us to say, all of these different websites, all of these different brands, they can take any content they want, whether it's text, images, videos, audio. We can create the right strategy for how we want to enable that to be searchable and discoverable and used in different AI applications, and have it be on a manageable system that scales very well and that enables very quick rollout of all of these different products. And we're really excited with many of the things that have been announced at MongoDB today and in the past year around AI. We think there are a lot of really great building blocks that MongoDB has provided that we're looking forward to putting those together and seeing how we can build out this next generation platform for our company.
That's great. So you're AI ready for the great unknown of AI, right? Chris, Tina, any parting words of wisdom? First of all, thank you so much, but any parting words of wisdom for the folks here in New York today that you wish to share?
I think I would say, I've heard some people complain that half of this conference seemed to be about AI and not necessarily MongoDB and database technology. Your talk notwithstanding. But I do think AI is something that we in the industry really should embrace. I know there have been a lot of tech fads that have come and gone. AI really does feel like something that is transformative. And I think the key thing, Frank Liu mentioned it in his keynote, the way that we as human beings interact with machines is now fundamentally changing thanks to AI. In the past, humans had to learn very odd, arcane ways to interact with computers. The very beginning of computer history is people putting dots into cards and feeding them into a machine to try to get it to do what we wanted it to do. And we've been getting better and better. We've invented programming languages, we've invented UX interfaces to get machines to do what we want, but for the first time, we're going to be able to interact with computers the same way we would interact with any other human being. And I think that's transformative both for how we work and also for the types of applications, the types of products that we're going to be able to offer our consumers. So I think it is the amount of time being spent on AI in this case is actually justified, and I encourage everyone to embrace that.
I'm just going to add to that. Yes, I say embrace AI. AI opens up new doors for us, but it's up to each one of us to build responsible, creative, futuristic solutions and systems.
Right. Chris and Tina, exceptional story, two exceptional people. Thank you so much for coming. We really appreciate it. Folks, let's give her a round of applause. Chris Chen, Tina Varghese, Condé Nast.
Thank you, everyone.
Thank you so much.